Okay, let's unpack this. When we talk about digital innovation, Bitcoin often captures the headlines.
It really does.
But our source material today, the original Ethereum Whitepaper from back in 2014 by Vitalik Buterin, it suggests Bitcoin's true genius wasn't just digital money. It was like the underlying tech, something potentially far bigger.
Exactly.
A foundation.
So our mission in this deep dive is really to get into this foundational document. We want to understand not just what Ethereum was meant to be, but why these ideas were so revolutionary, and what that still means for you, the curious learner. It really sets the stage for a world beyond just currency.
Indeed. And, the quest for a decentralized digital currency, it actually has a surprisingly long history.
Oh, yeah, before Bitcoin.
Absolutely. Early attempts back in the 80s and 90s, like anonymous eCash, they often stumbled because they relied on a central authority.
That central point of failure again. Precisely. Then came concepts like Wei Dai's B-Money in '98, which introduced computational puzzles, and Hal Finney's reusable proofs of work in 2005. Crucial steps, definitely, but still missing that complete, trustless solution.
So those early efforts, they were close, but didn't quite crack the decentralization nut. How did Bitcoin, when it finally launched in 2009, how did it solve that puzzle?
Well, Bitcoin's breakthrough was, frankly, ingenious. It combined public key cryptography, which gives you secure ownership, with this novel consensus mechanism called proof of work.
Proof of work. Okay.
And this wasn't just like a technical tweak. It was a fundamental shift. It allowed anyone to participate in validating the network without needing some central gatekeeper. It created a truly trustless digital money system. Basically, it swapped a formal barrier for an economic one. Your influence comes from your computing power.
Right. Okay. And from a technical view, the white paper describes Bitcoin's ledger as a state transition system. What does that actually mean in plain terms?
Okay, imagine it like this. The network has a current state. That's basically who owns what Bitcoin right now. A transaction is just a request to change that state. Alice wants to send money to Bob. The state transition function then takes the current state, applies Alice's transaction, and spits out a new updated state.
Simple enough.
If Alice has the Bitcoin, the transaction goes through, state changes. If not, error. Rejected. It's a very precise, very auditable way to track every single coin or fraction of a coin.
And in Bitcoin, that state isn't just a simple account balance, is it? It's more granular than that.
No, exactly. It's more specific. In Bitcoin, the state is the collection of all these things called unspent transaction outputs, or UTXOs.
UTXO.
Think of them like individual digital coins or bills. Each one has a specific value and an owner tied to a public key. When you spend Bitcoin, you're using these specific UTXOs as inputs.
Okay.
So say you have a 12 BTC UTXO and want to send 11.7 BTC. That 12 BTC UTXO gets consumed entirely. Right. And two new UTXOs are created, one for 11.7 BTC going to the recipient, and another for 0.3 BTC coming back to you as change.
Ah, okay. So it maintains that balance.
Exactly. The system meticulously checks. Do the input UTXOs exist? Is the signature valid? And crucially, is value conserved? Inputs must be greater than or equal to outputs.
So that's how individual Bitcoin transactions work, like Alice sending Bob money. But what makes it decentralized?
Yeah.
And secure across the whole world? How does everyone agree without a central bank? That's going to be the mining part.
Precisely. That's the magic, really.
Yeah.
Network nodes, miners, are continuously trying to mine new blocks. Think of blocks as packages of recent valid transactions.
Okay.
Each block contains, a timestamp, a reference hash pointing to the previous block, and the list of transactions. This linking creates the blockchain.
The chain.
And to make it secure, miners have to perform this proof of work. It involves doing a massive number of calculations, basically guessing a number, until they find a hash for their block that meets a certain difficulty target set by the network.
So it's computationally hard to do.
Extremely hard. And expensive in terms of electricity. This difficulty makes it incredibly tough to rewrite the blockchain's history. It prevents things like, the dreaded double spend.
Right. So how does Bitcoin specifically stop a double spend? Where, some attacker tries to spend the same digital coin twice.
Yeah, that's a really important question about security. The attacker's strategy would be send money to a merchant, get the goods shipped, maybe.
Right.
And then secretly try to create a different version of the blockchain, a fork, where they send the exact same money back to themselves instead.
Sneaky.
Very. But the network has one fundamental rule. The longest chain is truth. The chain with the most cumulative proof of work is the valid one.
Okay.
So for the attacker's fraudulent chain to be accepted, they'd need to outpace all the honest miners combined. That means controlling more than 51% of the entire network's computational power.
51%. That sounds like a lot.
It's huge. It makes a successful double spend incredibly difficult and, for most actors, prohibitively expensive.
Okay, that makes sense. Now, beyond security, the white paper mentions Bitcoin using something called Merkle trees for scalability. How do those work? How do they help?
Right, Merkle trees. They're essentially very clever digital filing systems inside each block. Instead of needing to process every single transaction to verify a block's integrity, they create a sort of hierarchical summary, a single root hash representing all the transactions.
An index.
Sort of, yeah. It allows data to be delivered piecemeal. So later nodes, these simplified payment verification or SPV nodes, they don't need the whole blockchain. They can just download BLI headers, verify the proof of work, and then request only the relevant branch of the Merkle tree needed to confirm a specific transaction. It's vital for long-term sustainability, especially considering how fast blockchains grow.
So Bitcoin laid this incredible foundation, right? Revolutionary. But it clearly had some, let's say, conceptual walls around it. Why did Vitalik Buterin and others look at this and think, okay, great start, but what if we could build more? Not just digital money, but like a universal digital computer, a trustless machine for any program. What were those key limitations that sparked the whole Ethereum vision?
That's the crux of it. Bitcoin did have a scripting language. It allowed for some basic smart contracts, like needing multiple signatures to spend funds.
I said, great.
Exactly. But it had some really significant limitations. For one, it wasn't Turing-complete, meaning it couldn't easily perform loops or complex iterative computations. Imagine trying to write any sophisticated software without for loops or while loops. It's incredibly restrictive.
Wow.
It was also value blind, meaning a script couldn't finally control the amount of Bitcoin being spent in complex ways. It lacked state, so contracts couldn't easily remember information or progress through multiple stages. And it was blockchain blind. Contracts couldn't access simple block data like timestamps or block numbers directly.
So those constraints really put handcuffs on what developers could actually build on top of Bitcoin itself.
Serious handcuffs, yeah. It severely limited the complexity and the scope of decentralized applications people were trying to build using alternative protocols or layers on top of Bitcoin, which often had their own issues.
So Ethereum's core vision was to just break those handcuffs, to open it all up.
Absolutely. Ethereum was pitched as an alternative protocol for building decentralized applications. It offered a different set of trade-offs aimed at rapid development, security for smaller apps, and crucially efficient interaction between different applications.
And the core innovation.
The core innovation is basically putting a blockchain with a built-in, fully-fledged Turing-complete programming language right at the base layer.
Turing-complete. There it is again.
That's the key. This allows anyone, in theory, to write smart contracts and decentralized applications dApps with arbitrary rules. Rules for ownership, transaction formats, state transitions, anything you can code.
So like Namecoin, that decentralized naming system you mentioned.
Right. The white paper points out you could essentially replicate Namecoin's basic functionality in just a couple of lines of Ethereum code. That power comes directly from embracing Turing completeness, plus making contracts value-aware, blockchain-aware, and giving them persistent state.
Okay, so instead of Bitcoin's very specific UTXO model, Ethereum introduced accounts. How do these work? What makes them fundamentally different? It sounds more like, well, a bank account.
That's a great analogy, actually. And if we connect this to the bigger picture, it is a paradigm shift. Bitcoin's UTXO model, it's like physical cash. A specific note is either spent or unspent. Ethereum's account model is much more like that bank account. Each account has a persistent balance of ether, a unique address, and this is crucial. If it's a contract account, it also has its own code and its own long-term storage, its memory.
So there are different types of accounts.
Two main types. Externally owned accounts, EOAs, which are controlled by private keys, like your typical crypto wallet, and contract accounts, which are controlled entirely by their own code once deployed. They become immutable.
Autonomous agents.
Exactly. That's a great way to put it. Contracts aren't just one-off conditions. They're more like these autonomous agents living inside the Ethereum system. They can hold ETH, store data, and interact with other accounts and contracts based on the rules in their code.
And how do these autonomous agents, these contracts, actually communicate and do things? The white paper talks about messages and transactions.
That's right. So an Ethereum transaction is what kicks things off externally. It's a signed data package sent from an externally owned account from a person with a private key. It includes the recipient address, the signature proving ownership, the amount of ether to send, maybe some data, and crucially, two fields: start gas and gas price.
Ah, gas. The fuel for Ethereum.
Precisely. Start gas is the maximum amount of computation the sender is willing to pay for, and gas price is the price per unit of computation per gas unit. This is Ethereum's core defense against denial of service attacks.
How so?
Well, because computation isn't free. You have to pay for every step the network takes to execute your transaction or contract code. This prevents someone from just deploying an infinite loop to try and clog the network because they'd run out of gas and money very quickly.
Makes sense. Pay for what you use.
Yeah.
And messages.
Messages are different. They're like internal transactions, but they're virtual, never serialized on the blockchain directly. They happen when one contract calls another contract's function.
Contract-to-contract communication.
Exactly. They work similarly to transactions, passing value, data, triggering code execution in the recipient contract, but they're initiated by code, not by an external user. This allows for complex interactions and applications built from multiple composable smart contracts.
Okay, let's get under the hood a bit more. How does Ethereum's core state transition function actually work? Give us the gist of how the network processes a transaction and updates everything.
Okay, at its heart, the system takes the current global state, all account balances, contract code, storage, and a transaction, TX. It applies the function APLYS, TX, and outputs a new state, S's.
Right.
The process is very systematic. First, check the basics. Is a transaction well-formed? Valid signature. Is the sender's nonce correct?
Nonce, like a transaction counter.
Exactly, prevents replay attacks. Then, calculate the maximum transaction fee, start gas price, and deduct it upfront from the sender's balance. Increment the nonce.
Okay, fee paid first.
Yep. Then, initialize the gas available for execution, deduct a base fee for the transaction bytes themselves, then transfer the ether value to the recipient account. If the recipient is a contract, load its code and execute it using the provided data, consuming gas for each computational step.
And if something goes wrong, like not enough ether or the code hits an error or runs out of gas.
That's the crucial part for atomicity. If the value transfer fails, like insufficient funds after paying the upfront fee, or if the execution runs out of gas at any point, all changes to the state made by this transaction are reverted. Except for one thing.
The fees.
The fees. The gas consumed up to the point of failure is not refunded. It goes to the miner who includes the transaction. Any remaining gas, if the execution finished successfully under the start gas limit, is refunded to the sender.
Ah, okay, so miners are incentivized to include transactions even if they might fail or run out of gas because they still get paid for the computation they performed.
Exactly. It prevents censorship and ensures even malicious or buggy code gets processed, but pays its way.
All this contract code, it's executed by the Ethereum virtual machine, EVM. It's not like running Python on my laptop, right? What's the EVM actually doing?
Right, definitely not Python. The EVM is essentially this global decentralized computation engine. It executes EVM bytecode, which is a low-level, stack-based instruction set. Think of it like the machine language for smart contracts.
Stack-based, like old-school programming.
A bit, yeah. It uses a stack for temporary calculations, memory for temporary data storage during execution, and then the persistent storage, which is like the contract's long-term hard drive, a key value store that lives on the blockchain state.
And every node runs this.
Every validating node, yes. When a transaction triggers contract code, the EVM on every node that processes that block executes the same code with the same inputs, ensuring they all reach the same resulting state. That's the core of the decentralized consensus on computation.
Now, the Ethereum blockchain itself also has some key differences from Bitcoin, particularly around state and mining. You mentioned state earlier.
Yeah, a really major difference is how state is handled in the blocks themselves. Ethereum blocks contain not just the list of transactions, but also the root hash of the most recent state tree.
The state tree, is that the Patricia tree thing?
Exactly. Bitcoin nodes typically have to replay all transactions from the Genesis block to figure out the current UTXO set, the current state. Ethereum uses this specialized data structure, a modified Merkle-Patricia tree, which allows for efficient updates and proofs.
How does that help?
It means that the state root hash in the block header acts as a secure fingerprint of the entire system state after all transactions in that block have been applied. Nodes only need the most recent state and the blocks to verify everything. They don't necessarily need to store or replay the entire history from day one just to stay in sync.
So what does this all mean practically? Unlike Bitcoin, Ethereum full nodes don't absolutely need the whole history just to validate new blocks, just the current state. That sounds like a massive game changer for storage.
It is, potentially, precisely. This design, especially with the Patricia tree efficiently handling updates, can offer significant savings in storage space compared to, say, applying the same idea directly to Bitcoin's UTXO model. It makes running a full node less burdensome over time. And as we touched on, it ties into validation. Verifying a block inherently involves executing the transactions and confirming the resulting state root matches the one in the header. Contract execution is part of validation, done by all nodes.
Okay, now that we've got a handle on the mechanics, let's zoom out to the vision again. The white paper outlines sort of 3 broad categories for what you could do with Ethereum.
Yes, it lays out a pretty exciting landscape. The first category is purely financial applications, things like derivatives, hedging contracts, wills, maybe even complex employment agreements that pay out automatically based on conditions.
Makes sense. Crypto's roots.
Second, semi-financial applications. These involve money, but also have a big non-monetary side. Think self-enforcing bounties for solving computational problems, or perhaps incentivizing data submission. And the third category is non-financial applications. This is where it gets really broad. Things like online voting systems, decentralized governance like DAOs, identity and reputation systems. Things far beyond just moving money.
Let's dig into a few specific examples the paper highlights. Token systems, for instance. These are ubiquitous now. But how simple were they envisioned on Ethereum?
Incredibly simple, fundamentally. At its core, a token system is just a database, right? A ledger mapping addresses to balances.
Yeah.
On Ethereum, you can write a basic smart contract with essentially one core function, send to value. This function just checks if the sender, MSG sender, has enough tokens, subtracts the value from the sender's balance in the contract storage, and adds it to the recipient's to balance. That's it.
Wow.
That simple contract living immutably on the blockchain enforces the rules of your custom token. The white paper even suggests ways to let users pay transaction fees in the token itself by having the contract refund the sender Ether from its own holdings.
What about financial derivatives and stablecoins? We see them everywhere now. The white paper saw this coming.
It definitely anticipated the potential. Financial derivatives are a very natural fit for smart contracts, which can automatically execute based on predefined conditions. The main challenge, even back then, was identified: getting reliable external data onto the blockchain. Price feeds, mainly.
The Oracle problem.
Exactly, the Oracle problem. The paper gives an example of a hedging contract. Alice and Bob deposit Ether. After 30 days, the contract queries an oracle for the ethist price and automatically distributes the funds to hedge one party against volatility relative to the other. It showed how you could create these instruments without a central issuer, though you still often need a trusted data source, the oracle.
And identity systems, like Namecoin, which existed before Ethereum. How does Ethereum improve on that?
Well, Ethereum provides a much more flexible and general platform for them. A very simple identity contract could just let someone register a unique name to their address, like self.storage name and value. First come, first served.
Basic registration.
Yeah, but you could easily build much more complex systems on top. Add functions for transferring ownership, maybe link reputation data stored in another contract, create more sophisticated namespaces. The programmability is key.
Okay, another really intriguing one is decentralized file storage. That sounds ambitious, taking on giants like Amazon S3 or Dropbox.
Yeah, it's definitely ambitious. The white paper points out the inefficiencies in traditional cloud storage pricing and structure. The idea with Ethereum is to use contracts to coordinate a whole decentralized ecosystem. Users could essentially rent out their unused hard drive space.
How would that work securely?
Well, the concept involves splitting data into chunks, encrypting it, maybe using erasure coding for redundancy, and then building a Merkle tree over it. You distribute these chunks to different storage providers, farmers.
Okay.
The contract then periodically challenges these providers. It might pick a random index in the Merkle tree and reward the first node that provides the correct chunk and its proof of inclusion. To retrieve your file, you'd use something like a micropayment channel to pay providers as you download chunks.
So the contract enforces the storage agreement.
Exactly. It uses cryptographic proofs and economic incentives to create a potentially more resilient, efficient, and maybe even private storage network then centralized options.
And then there's the really mind-bending one. Decentralized autonomous organizations, or DAOs. What exactly are these virtual entities?
DAOs are, well, they're essentially organizations that live entirely in code on the blockchain. They have members or shareholders who collectively control the organization's funds and can even vote to modify its own code, its rules.
Like a company run by code.
Kind of, yeah. Imagine a company or a nonprofit where all the bylaws, the treasury management, the decision-making processes are encoded in smart contracts. Decisions like spending funds or changing memory rules might require a certain percentage vote, say 67% of shareholders, to pass.
No CEO, no board meetings in a stuffy room.
Potentially, yes. The code is the governance structure. The white paper contrasts a DAC, decentralized autonomous corporation, maybe more capitalist, with a community model. It outlines how you could code this using separate contracts for logic and storage, allowing the logic contract address to be updated via voting. It can handle proposals, voting periods, execution thresholds, even sophisticated things like liquid democracy, where you can delegate your voting power to someone you trust on specific issues.
It's a lot to take in. Beyond these big examples, the white paper just rattles off even more possibilities, right? Just to show the breadth.
Yeah, it's like a rapid-fire brainstorm at the end. Things like savings wallets with withdrawal limits, maybe requiring cosigner approval, crop insurance using weather data feeds as oracles to trigger payouts automatically after a drought, decentralized data feeds themselves using game theory like Shelling Coin to incentivize truthful reporting, smart multi-signature escrow with super granular conditions, even cloud computing markets.
Cloud computing on Ethereum.
The idea is verifiable computation. Someone requests a task, others perform it, and provide a proof, potentially checkable within the EVM or via spot checking, that they did it correctly. You could use security deposits to ensure honesty. Good for tasks that are easy to parallelize, like SETI at home was mentioned as an analogy.
Yeah.
Plus, things like peer-to-peer gambling, prediction markets, decentralized marketplaces. The list just goes on. It really paints a picture of a general-purpose platform.
This incredible flexibility, this ambition, it obviously comes with challenges. The white paper doesn't shy away from those. One big one is handling fast block times. How do you do that without wrecking security? You mentioned something called Ghost.
Right, Ghost. This is a critical point. If you make block times really fast, say a few seconds instead of Bitcoin's 10 minutes, you naturally get more stale blocks. These are blocks that were mined correctly, but just didn't make it into the main chain because another block got propagated slightly faster.
Wasted work.
Exactly, wasted work. And it can actually centralize mining because larger pools have an advantage in getting their blocks propagated quickly. The Ghost protocol, which stands for Greedy Heaviest Observed Subtree, is a way to mitigate this. The basic idea is to change the rule for determining the longest, or main chain. Instead of just counting blocks in a line, you also give some weight to these stale blocks, these uncles that attach to the main chain.
So uncles count for something.
In Ethereum's modified version, yes. Including an uncle block gives a small reward to the uncle miner, like 87.5% of the base reward, and a bonus to the nephew block miner who includes it, 12.5%. Transactions in uncles aren't executed, though. This mechanism helps secure the network with faster block times by reducing the penalty for finding a block slightly late and discouraging centralization.
Okay, what about transaction fees? Bitcoin's fee model has had issues. Ethereum aims to fix the tragedy of the commons problem, where every transaction costs the whole network resources, not just the miner.
Yes, this is a subtle but important economic point. If fees are purely voluntary or only benefit the miner directly, there's less incentive for the miner to consider the cost their included transactions impose on every other node that has to store and process them.
Right.
Ethereum's solution involves that gas mechanism we discussed, but also a dynamic block gas limit. This isn't a fixed limit. It's adjusted by miners voting on it implicitly with each block they produce, targeting an average gas usage over time. It allows the network capacity to fluctuate based on demand, but keeps it within bounds that the network can collectively handle, regulating the overall computational load.
And then there's that elephant in the room with Turing-completeness, the infinite loop problem. Giving a global computer the power to run any program sounds amazing, but also terrifying. What stops someone crashing the whole thing with a program that just never stops?
Right, the halting problem. It's a fundamental limit of computation. You can't perfectly predict if an arbitrary program will halt or run forever. For a decentralized network, that's potentially catastrophic. An attacker could try to launch a logic bomb transaction that consumes infinite resources.
So how did Ethereum solve it?
The solution, again, boils down to gas. the start gas limit. Every transaction must specify the maximum gas it's allowed to consume. When the EVM executes code, each instruction costs a specific amount of gas. If the total gas consumed exceeds start gas, the execution halts immediately.
Okay, it stops. But what happens then?
Crucially, all state changes made by that transaction's execution are reverted, wiped clean as if it never happened. However, the fees for the gas that was consumed up to that point are still paid to the miner.
Ah, so the attacker's infinite loop costs them money, achieves nothing state-wise, and the miner still gets paid for the work done.
Exactly. It elegantly sidesteps the halting problem by making infinite loops economically infeasible and non-disruptive to the network state, while still incentivizing miners to include and attempt execution of any valid transaction.
So the white paper basically argues that going for full Turing completeness, despite the risks, is actually more manageable than trying to perfectly prevent it. Can you elaborate on why?
This is a really interesting point they make. The argument is that trying to create a system that is definitively not Turing-complete but still powerful enough to be useful is surprisingly difficult and might even be impossible without similar safeguards anyway.
How so?
Well, even if you ban explicit loops, clever programmers could potentially simulate them, maybe by creating a long chain of simple contracts that call each other sequentially, or by using dynamic dispatch where a contract calls another contract whose address isn't known until runtime, potentially leading to complex, resource-intensive interactions.
So you'd still need something like gas limits to prevent those kinds of exploits.
Pretty much, yeah. Since you likely need gas limits or similar computational metering mechanisms anyway to handle complex interactions and prevent resource exhaustion, the white paper argues you might as well embrace full Turing completeness and gain all the expressive power that comes with it. The necessary safety mechanisms are largely the same.
Let's switch gears slightly to Ether itself, the currency. What's its fundamental purpose in the system, and how was it initially issued?
Ether really has two main jobs. First, it's intended to be the primary native liquidity layer for exchanging various digital assets and paying for services within the Ethereum ecosystem. Second, and perhaps more technically crucial, it's the mechanism for paying transaction fees, the gas we keep talking about. It's the fuel needed to run the decentralized computer.
And the issuance.
Yeah.
How did Ether come into existence?
The initial supply was distributed through a public currency sale back in 2014-2015, which funded the nonprofit Ethereum Foundation and core development. After the network launched, the plan outlined in the white paper was for ongoing issuance to miners. A fixed amount, equal to 0.26 times the amount sold in the initial sale, would be created each year forever.
Forever. Unlike Bitcoin's capped supply. Why?
The justification was twofold. First, a constant linear issuance was argued to reduce the risk of excessive wealth concentration that might occur with a strictly capped supply like Bitcoin's. Second, it ensures that there's always some way for future users and generations to acquire Ether through mining or later staking, maintaining a degree of ongoing distribution. Importantly, while the absolute issuance is constant, the percentage rate of supply growth still tends towards zero over the very long term.
And the white paper mentioned a potential future switch away from mining.
Yes, it explicitly mentioned the plan to eventually move to a proof-of-stake consensus mechanism, which was expected to potentially come with significantly reduced issuance rates. It framed this as part of a social contract, the idea that the protocol could evolve over time based on community consensus. And of course, that switch to proof-of-stake has now happened.
Okay, final challenges. Scalability and mining centralization. Bitcoin has definitely faced issues with specialized ASIC hardware dominating mining, and large pools controlling huge chunks of the network power. How did Ethereum plan to tackle this from the start?
This was a major design consideration. Bitcoin's SHA-256 algorithm proved very amenable to optimization via ASICs, application-specific integrated circuits, which quickly priced out hobbyist miners using GPUs or CPUs. This led to centralization concerns.
Right.
Ethereum's initial mining algorithm, Ethash, was deliberately designed to be memory hard. It required miners not just to perform computations, but also to fetch large amounts of fairly random data from a multi-gigabyte dataset derived from the blockchain state itself.
Why memory hard?
The idea was that the bottleneck would be memory bandwidth and capacity, not raw processing power. This makes designing a specialized, significantly more efficient ASIC much harder and more expensive. An Ethereum ASIC, the theory went, would end up looking quite a lot like a general-purpose computer, with lots of fast memory closer to a high-end GPU. This aimed to keep mining more accessible and decentralized. Plus, Needing access to the blockchain state inherently encouraged miners to run full nodes.
Clever. And what about overall scalability? We know processing every transaction on every node is a bottleneck for Bitcoin. Ethereum faces the same fundamental issue, right?
It absolutely does. The white paper acknowledges this limitation directly. Processing thousands of transactions per second, like Visa, would generate enormous amounts of data if every node had to process everything synchronously on layer 1. This inevitably leads to centralization pressure. Only those with substantial hardware can run full nodes, leaving others reliant on lighter clients.
So what were Ethereum's initial thoughts on mitigating this?
Well, one mitigation, as we discussed, is that nodes primarily need to store the state, not necessarily the entire history, thanks to the Patricia tree structure that helps manage storage growth. The white paper also discussed forcing miners to be full nodes via the mining algorithm. Beyond that, it touched on more advanced concepts, like using intermediate state roots within blocks to allow for proofs of invalidity, where verifying nodes could efficiently prove a block was bad, and even challenge response protocols for light clients to gain higher security assurances without downloading everything. These ideas laid groundwork for later Layer 2 scaling solutions.
As we've really dug into this document today, it's pretty astounding. The sheer foresight laid out nearly a decade ago. It's a vision that has genuinely reshaped large parts of the digital world, taking us so far beyond just peer-to-peer cash.
Absolutely. And if you connect it to the bigger picture, it's clear Ethereum wasn't just meant to be another cryptocurrency. It was conceived right from the start as this generalized computing platform, a foundational layer for decentralized applications. Its open-ended, programmable nature allows for systems and interactions that, frankly, probably weren't even fully imagined back in 2014. It aimed to bring computational efficiency and a robust economic layer to all sorts of peer-to-peer interactions.
The Ethereum whitepaper really stands as a testament, doesn't it? How a single, deeply thought-out document can lay down the core principles for a technology that just keeps evolving, keeps disrupting, even as it confronts entirely new challenges along the way. For you, the curious learner listening, maybe consider, what other foundational documents, perhaps being written right now, might be sketching out the next wave of innovation? And what fundamental questions might they raise for you about the shape of our digital future?